Look up at the night sky. Find the darkest patch between the stars, a place where nothing seems to exist. Now I want you to imagine the most powerful, the most terrifying, the most absolutely indestructible object in the entire universe. A place where gravity has won. A place where space itself is torn. Time stops and light is swallowed forever. A black hole. The universe's ultimate vault. Nothing, we are told. Nothing can ever escape its pull. Not a bullet, not a rocket, not a single whisper of light. It is a one-way door to oblivion. It is eternal. It is permanent. It is the end of this story. Now, forget all of that, because I am going to tell you something that sounds like complete and utter nonsense. That black hole, that cosmic monster, is evaporating. Right now, it is fading away, particle by particle, into nothingness, and it will eventually, inevitably vanish in a final silent puff of radiation. It has a lifespan. It is mortal. And the reason why, the true reason why, has nothing to do with gravity and everything to do with empty space. The void itself is alive, and it is slowly, patiently dismantling the universe's most perfect trap. This seems impossible. It contradicts everything you think you know. And by the end of this journey, you will not only believe it, you will see that the universe had no other choice. You see that for a black hole to exist at all, it must, by the deepest laws of reality, eventually evaporate. And the key to this revelation came from a path laid down by Richard Feynman, a way of seeing the quantum world that turns our intuition inside out. This is not a small idea. This is a fundamental collapse of everything we assume about permanence and destruction. Stick with me. I promise you, by the time we reach the final piece of this puzzle, your understanding of reality will have shifted. Now, if that opening claim made your brain itch a little, if it sparked a sense of, wait, that can't be right, but I need to know, then you are exactly where you need to be. That feeling is the fuel for this entire channel. This is Think Beyond Physics, and if you're new here, welcome. What we do here is simple, but it requires patience. We take one single seemingly impossible idea in physics and we don't just skim it, we dismantle it, we sit with it. We walk the long, winding path that the greatest minds walked, from confusion to breakthrough. We chase that itch. And if that's the kind of deep, satisfying understanding you've been looking for, then you should consider subscribing. Because here, we don't just give you facts, we rebuild your intuition. We treat you like a fellow thinker, not just a viewer. So to those of you staying, and I sincerely hope you do, thank you. You've chosen to engage with the mystery, and that choice puts you in a rare group. You're not here for quick answers. You're here for real ones. And I promise you, the answer to how a black hole, the very definition of an inescapable pit, can possibly evaporate, is more strange, more beautiful, and more fundamental than any sci-fi tale. It forces us to ask, what is nothing? What does it mean for a particle to exist? And how can the rules of the very small possibly dismantle the rules of the very large? This is not a story of destruction. It is a story of transformation, written into the fabric of reality itself. So let's begin where all good detective stories begin, not with the answer, but with the seemingly unshakable truth that is about to be broken. So what is it that everyone thinks they know? Let's build the picture together. Imagine with me a star much larger than our sun. It lives, it burns through its fuel, and eventually the nuclear furnace in its core can no longer fight the immense weight of its own outer layers. It collapses, not just a little. It falls inward at a significant fraction of the speed of light. The density becomes unimaginable. The gravity becomes so intense that at a certain point, a point of no return is crossed. We call this the event horizon. It is not a physical surface, not a hard shell of matter. It is a mathematical boundary in space. A point of no return. Think of it like a waterfall. Far upstream, the river flows smoothly. You can paddle against the current. But as you get closer to the edge, the current becomes stronger and stronger. There's a critical point where the current's velocity exceeds the fastest you can possibly paddle. That line is your event horizon. Cross it, and no matter how powerful your engine, you are going over the falls. For a black hole, the current is the curvature of space-time itself. The paddling is the speed of light. Nothing can move faster than light. Therefore, once you cross that boundary, every possible path, every future, leads inexorably downward to the center, to the singularity. This is the classical picture, the one Einstein's theory of general relativity gives us, and it is breathtakingly elegant and absolute. It says, what goes in does not come out. A black hole, once formed, is a stable, permanent fixture. It can only grow. It can only get more massive as it swallows more gas, more stars, more light. It is the universe's ultimate sink. This feels logical. It feels inevitable. It feels permanent. But here is where we must introduce our first quiet crack in this monolithic intuition. Let's play with this classical picture for a moment. Imagine you have a black hole, and you decide to throw things into it. You throw in a bucket of hot gas. You throw in a hard drive full of encrypted data. You throw in a perfectly crafted diamond in a bag of burnt, disordered ash. From the outside, what happens? According to the classical rules, the black hole just gets more massive. Its gravity increases slightly. The event horizon swells a little. But all the other properties of the things you threw in, the temperature of the gas, the intricate information on the hard drive, the perfect order of the diamond versus the disorder of the ash, all of that is gone, swallowed, hidden behind the horizon, forever. The black hole, to an outside observer, is described by only a few simple numbers. Its mass, its electric charge, and its spin. That's it. This is sometimes called the no-hair theorem. A black hole has no hair, no intricate details, no individuality beyond those few parameters. So, if you take a universe full of beautifully complex, unique arrangements of matter and energy, and you feed them all into black holes, you end up with just a few simple numbers floating in the void. Where did all the complexity go? Where did the information about what made those things unique go? This is our first what moment. Because in physics, we have deep-seated beliefs, almost instincts, about how the universe works. One of the most cherished is the principle of conservation of information. It's related to cause and effect. In a deterministic universe, if you know the exact state of everything now, you should, in principle, be able to calculate the state of everything in the past or the future. Information, the specifics of what is, what cannot just vanish. It can be scrambled, like an egg, but it must still be there in some form. Throwing a hard drive into a fire scrambles it into heat and smoke, but in principle, if you could track every atom and photon, you could reverse the process and reconstruct the data. But a classical black hole seems to be a one-way street to information destruction. It's the ultimate shredder, and the shreds are trapped forever behind a wall we can never see past. This makes physicists profoundly uncomfortable. It's not just a puzzle, it feels like a violation of something fundamental. This crack, this tension between the beautiful deterministic gravity of Einstein and the ingrained principles of the rest of physics is the first hint that the story is not over. The black hole, in its classical perfection, might be hiding a fatal flaw, and to find it, we will have to leave the realm of the very large, the realm of planets and stars and gravity, and dive into the chaotic, probabilistic, utterly bizarre realm of the very small. The realm where empty space is never empty. The realm where something can come from nothing. To understand how we got from the permanent classical black hole to an evaporating one, we have to take a journey back in time. Not to the age of dinosaurs, but to a period of intellectual ferment, just as dramatic the first half of the 20th century. This is a human story, full of wrong turns, stubbornness, and flashes of insight so bright they illuminated corners of reality we never knew existed. Our story doesn't begin with black holes. It begins with a crack in the air, a sense that the foundation of physics was splitting in two. On one side, you had Albert Einstein. By 1915, he had given us general relativity, a theory of gravity so beautiful it felt like it was written in the geometry of the universe itself. Gravity wasn't a mysterious force reaching across space. It was the curvature of spacetime itself. Matter and energy told spacetime how to curve. Curved spacetime told matter how to move. It was a perfect deterministic dance. If you knew the state of the universe at one moment, the equations would tell you its state at any other moment. It was a cosmos of certainty, a cosmic clockwork. On the other side, bubbling up in the 1920s, was quantum mechanics. This was not a theory of the large and majestic, but of the small and furious. It was born in the chaos of the atomic world, and it was everything general relativity was not. Where relativity was deterministic, quantum mechanics was probabilistic. It didn't tell you where an electron was. It gave you a cloud of possibilities for where it might be. It introduced fundamental uncertainty, not as a limitation of our instruments, but as a property of reality itself. Its heroes were figures like Niels Bohr, Werner Heisenberg, and a young, brilliantly intuitive Richard Feynman. This world was not smooth and geometric. It was jumpy, grainy, and ruled by chance. And it worked with spectacular precision. It explained the structure of atoms, the glow of heated metal, the very existence of chemistry. And here was the problem. These two towering pillars of modern physics, each magnificently successful in its own domain, were speaking completely different languages. They were built on philosophies that were directly opposed. For decades, most physicists lived with this split personality. You used quantum mechanics for the small, atoms, particles, and general relativity for the large, stars, galaxies. You never really needed to use them together. It was an uneasy truce. But in the 1960s, a location was discovered where this truth was impossible to maintain: the singularity at the heart of a black hole and the event horizon that surrounded it. Here, enormous mass was crushed into an infinitesimally small point, a domain where the rules of the very large and the very small had to collide. The mathematical solutions describing black holes were pure general relativity, but anyone thinking deeply knew that near that singularity, quantum effects must become monstrously important. It was a frontier, and it needed a new kind of thinker. Enter John Archibald Wheeler. Wheeler was a physicist with the mind of a poet and the courage of a philosopher. He coined the term black hole in 1967, giving a name to these mysterious gravitational collapses. He pushed his students to ask the deepest, most embarrassing questions. And he was one of the first to seriously grapple with the implications of throwing quantum stuff into a classical black hole. He saw the information problem brewing. He famously summarized the paradox of the no-hair theorem with a provocative phrase: "A black hole has no hair." But he also crucially began asking, what does quantum mechanics do to the horizon? He didn't have the answer, but he framed the question in a way that would haunt a generation. Now, let's zoom in to the early 1970s. A young physicist named Stephen Hawking was making a name for himself by applying powerful new mathematical techniques to the theory of black holes. He had already proven with Roger Penrose that singularities weren't just mathematical oddities, they were inevitable, endpoints of gravitational collapse under general relativity. Hawking was deeply immersed in the classical, beautiful world of Einstein's equations. He believed in the permanence of black holes. In fact, in 1970, he formulated what became known as the second law of black hole mechanics, which essentially stated that the total area of the event horizons in the universe can never decrease. A black hole can merge with another, making a bigger one, but it can never split or shrink. This fit perfectly with the classical permanent picture. It even looks suspiciously like the second law of thermodynamics, which says disorder, entropy, always increases. But Hawking and others saw this as a curious analogy, not a literal connection. Black holes, they thought, were cold, perfect geometric objects. They had no temperature. They could not radiate. The stage was now set for the revolution, and it happened almost by accident. In 1972, a physicist named Jacob Bekenstein, a bold graduate student of Wheeler's, made an outrageous suggestion. Wrestling with the information paradox, he looked at Hawking's area increase law and the thermodynamics entropy increase law and said, what if this isn't just an analogy? What if the area of the horizon is a measure of the black hole's entropy? This was heresy. Entropy is a measure of disorder, of hidden information. For a black hole to have entropy, it must have an internal structure, a way to store all that scrambled information about what fell in. More shockingly, if it has entropy, then by the rigid laws of thermodynamics it must also have a temperature. Anything with a temperature radiates. But how can a black hole, the ultimate absorber, radiate? Hawking thought this idea was preposterous. He spent the next year trying to disprove it, to defend the pure classical picture. And here is where the story turns. In 1973, Hawking traveled to Moscow, where Soviet physicists Yakov Zederich and Alexei Starobinsky convinced him that according to quantum mechanics, a rotating black hole should indeed create and emit particles. This was a shock. Hawking returned to Cambridge, his mind racing. He set out to prove that while a rotating black hole might have this quantum trick, a normal non-rotating one would not. He dove into the murky, newly developing theory of quantum fields in curved spacetime, the first real attempt to stitch the two great theories together. He worked through the mathematics tracing what would happen to the quantum fields that permeate all of space as they approach the terrifying edge of an event horizon. The calculation was grueling, but the result was unmistakable. It hit him with the force of a physical blow. A non-rotating black hole sitting alone in the void wasn't just cold and dark. The intense curvature of space at its event horizon would fundamentally alter the quantum soup of virtual particles that fizz in and out of existence everywhere. And it would do so in a way that would cause the black hole to glow. Not with light from inside escaping, but with new, real particles born at the horizon itself, carrying energy away into space. The black hole would lose mass. It would shrink. Hawking had not only confirmed Bekenstein's wild idea, he had given it a precise, calculable mechanism. The black hole had a temperature inversely proportional to its mass. A small black hole would be hotter, evaporating faster in a frenzied burst. A giant one would be icy cold, evaporating over time scales longer than the current age of the universe, but evaporating nonetheless. In December 1973, he knew he was right. The discovery, he would later say, was the most surprising and beautiful of his career. He had set out to kill an idea and had instead given it life. He announced it at a conference in February 1974, and the physics world was divided between awe and disbelief. He had taken the two warring theories, quantum mechanics and general relativity, and forced them to speak to each other at the most extreme frontier. And what they said changed everything. The permanent vault was leaking. The universe's ultimate sink had a drain, and the drain was powered by the restless energy of nothingness itself. Now we arrive at the core of the mystery. We had the historical fact Stephen Hawking calculated that black holes must radiate, but a fact without understanding is just a piece of trivia. We want to see it. We want to feel in our bones why this must happen. How can the void around a black hole become a furnace? To get there, we have to rebuild our understanding of what nothing really is. And for that, we're going to take a page from Richard Feynman's playbook. Feynman didn't just teach equations, he taught a way of seeing. He would ask, what is really happening? And to answer that, we need a series of mental images, each one taking us a layer deeper. Let's start with a thought experiment that has nothing to do with black holes, but everything to do with quantum reality. I want you to imagine a perfectly flat, perfectly calm pond. The water is so still it looks like glass. This is our analogy for the vacuum of space in the quantum world, what we classically think of as pure, empty nothingness. Now, according to quantum field theory, this nothing is not still. It is a seething, bubbling foam of potential. Everywhere at all times, pairs of particles and their opposite antiparticles are spontaneously flickering into existence. We call these virtual particles. They borrow energy from the universe, exist for an unimaginably short blink of time, and then annihilate each other, paying the energy back. This isn't just a guess. It's a proven consequence of the Heisenberg uncertainty principle, which allows for tiny violations of energy conservation so long as they happen fast enough. So our calm pond, if we look with quantum eyes, is actually a chaos of tiny ripples constantly appearing and disappearing. Most of the time, these ripples cancel each other out perfectly, and from a distance the pond looks calm. This is our new baseline. The vacuum is alive. Now, let's introduce a gentle, steady wind blowing across the pond. This wind represents a force field like an electric field. What happens to our virtual ripples? Something fascinating. The wind can catch these temporary ripples and, if conditions are just right, give them enough of a nudge to separate them. Instead of the particle and antiparticle ripples collapsing back into each other immediately, the wind blows them apart. Once they are separated beyond a critical distance, they can no longer find each other to annihilate. They become real. They have to pay back the energy they borrowed, but now the energy comes from the force field itself, which weakens slightly as a result. This is a real, measurable phenomenon in strong electric fields called the Schwinger effect. It's the universe creating something from nothing powered by an external field. Remember this image. Temporary fluctuations made permanent by an external influence. Now let's trade the pond for the black hole, and let's trade the gentle wind for the most extreme environment imaginable, the event horizon. But here's the critical shift. The key player at the horizon isn't a force like electricity, it's the curvature of space-time itself, gravity, so strong it defines the edge of reality. To understand its effect on our quantum foam, we need another thought experiment, one that focuses on the nature of time. Imagine two intrepid quantum astronauts, Alice and Bob. They are floating in the calm vacuum of space, far from any gravity, and they are holding the world's most sensitive particle detector. It registers nothing. The vacuum is, to them, truly empty. Now Alice decides to embark on a journey. She gets into a rocket and begins to accelerate. She fires her engines constantly so she feels a steady force, a fake gravity, if you will. As she accelerates, something strange happens. Her particle detector begins to click. It is registering particles, real, warm photons streaming past her. From her perspective, the once empty vacuum now feels like a warm bath of radiation. Bob, who is still floating freely, still sees nothing. This is not a detector malfunction. This is a profound phenomenon called the Unruh effect. Acceleration through the quantum vacuum creates particles. Why? Because the definition of a particle is not absolute. It depends on your state of motion, what one observer calls empty. Another observer, accelerating through that same space, calls a plasma of particles. The act of accelerating, of having a horizon behind you that you can never go back to, literally heats up the vacuum. Now, connect the dots. What is the event horizon of a black hole? It is the ultimate point of no return. But for someone just outside the horizon, space-time is curved in such a way that to stay in place, to avoid falling in, you must accelerate. You must fire your rockets constantly just to hover. In fact, the The closer you get to the horizon, the harder you have to accelerate to stay still. And as we just learned from Alice, acceleration makes the vacuum glow. So for someone hovering near the black hole's horizon, the quantum vacuum isn't empty. It is a firestorm of radiation. This is the first intuitive step toward Hawking radiation. The intense gravitational acceleration near the horizon heats the quantum foam. But that's only half the story. It explains why there's energy there, but not how the black hole loses mass. For that, we need our most famous and often most misunderstood image, the virtual pair at the edge of the abyss. Picture, again, a pair of virtual particles flickering into existence right at the event horizon. In the usual vacuum, they would annihilate. But here, the extreme gravity of the black hole can act like the wind on the pond. In one version of the story, a helpful but slightly flawed cartoon, one particle of the pair falls into the black hole, while the other escapes to infinity. The escaping particle becomes real, carrying positive energy away. Its partner, falling in, carries negative energy relative to the outside universe. When this negative energy particle falls into the black hole, it reduces the black hole's total mass energy. The black hole pays for the creation of the escaping particle by losing a tiny bit of its mass. Now, I must pause here. This particle pair picture is a beautiful, intuitive cartoon, and it's how Hawking himself often explained it. But it's a simplification. The true, mathematically rigorous description doesn't involve individual particles jumping out. It involves the quantum fields themselves being in a state where, far from the black hole, they contain a steady thermal flux of real particles. The cartoon, however, captures the essential mind-bending trade. The black hole's gravitational energy is being used to promote quantum fluctuations into real particles at the cost of its own mass. Let's test this intuition with a direct objection you might be having. If the particle is coming from outside the horizon, how is the black hole losing mass? It's not like matter is coming out from inside. Think of it this way. The black hole's mass is not locked in a vault at the center. Its mass is in its gravity field. The entire curved spacetime around it is the manifestation of its mass. By creating a real particle that flies away from that curved spacetime, you are effectively extracting energy from the gravitational field itself. You are, in a very real sense, shaving a tiny bit of curvature off the universe. The field weakens imperceptibly, and that weakening is the black hole getting lighter. But wait, there's another huge question. You might remember that virtual particles borrow energy. If one falls in and the other escapes, hasn't the energy loan been repaid? How does that reduce the black hole's mass? This is where the negative energy concept is key. In the context of general relativity, energy is a tricky thing to define locally in a curved spacetime. But we can think of it this way. The particle that falls in is on a trajectory that, from the perspective of the distant universe, has less energy than if it had never existed at all. Its addition to the black hole interior is like adding a hole of energy. It's subtractive. The accounting works out. The positive energy of the escaped particle is balanced by the negative energy of the infalling one, and the black hole's books show a deficit. Its mass decreases by the amount of energy that flew away. Now let's go deeper. What determines the temperature of this radiation? Why is a small black hole hot and a large one cold? Think back to the acceleration analogy. The required acceleration to hover at the event horizon is inversely proportional to the black hole's size. A small black hole has an incredibly small event horizon, and the gravity right outside it is ferociously strong. To hover there, you'd need to accelerate at an unbelievable rate. And as Alice taught us, higher acceleration means a hotter thermal bath. So a small black hole has a fiercely high unrule-like temperature at its horizon, meaning it radiates high-energy particles at a rapid rate. A giant, supermassive black hole has a much gentler curvature at its enormous horizon. The required acceleration is small. The thermal bath is frigid, barely above absolute zero. It radiates away pathetic low-energy photons over incomprehensible eons. The temperature formula Hawking derived captures this perfectly. The temperature is inversely proportional to the mass. Let's solidify this with a concrete, numerical shock to anchor the scale. Imagine a black hole with the mass of our sun. Its event horizon would be about 3 kilometers across. Using Hawking's formula, its temperature would be about 60 nanokelvins. That's 60 billionths of a degree above absolute zero, colder than the deepest depths of space. It would absorb far more cosmic microwave background radiation than it emits. It would grow, not shrink. Now, imagine a small black hole with the mass of a mountain, say, 1 billion tons. Its event horizon would be smaller than an atomic nucleus. Its temperature? About 1 trillion kelvins. It would be a screaming furnace of gamma rays and particles, evaporating in a fraction of a second in a titanic explosion. This is the shocking range. Size determines fate. The universe's mightiest monsters are, in terms of their quantum glow, inert icebergs. The tiny hypothetical ones are the cosmic fireworks. We've explained the how in a mechanical sense, but the deepest layer of understanding comes from connecting this to the most fundamental principles. Remember the crack we opened earlier, the information paradox. Hawking's calculations showed that the radiation coming out is purely thermal. It has a temperature, but it carries no other information. It's like the featureless glow of a hot piece of coal. It doesn't matter if the coal was made from oak, pine, or plastic. When it's hot, it glows the same. According to Hawking's original work, if you feed a black hole a perfectly ordered diamond in a random pile of trash, the Hawking radiation that eventually evaporates it would be identical in both cases. All the unique, intricate information about what fell in is lost forever, burned away into a random thermal mush. This was Hawking's own terrifying conclusion. He believed for decades that his radiation implied a fundamental breakdown of quantum mechanics' rule that information can never be lost. This was the black hole information paradox in its starkest form. So now we have two revolutions wrapped into one. First, black holes evaporate a stunning merger of gravity and quantum theory. Second, their evaporation seems to destroy the very fabric of cause and effect by erasing information. For decades, this was the unsettling trade-off. Yes, black holes were mortal, but the cost was the purity of quantum law. It set off a war in theoretical physics that is still echoing today. And it leads us to the final unifying truth. Because the story doesn't end with Hawking's 1974 calculation. The most modern chapters suggest that the information might not be lost at all. That it is, in some way, we are still struggling to visualize, preserved in the radiation itself, that the evaporation might be a spectacularly complex transformation, not a deletion. And to glimpse that, we have to ask what happens in the final moments, and what the true nature of the horizon might be. So here we stand, at the precipice of understanding. We have followed the trail from the absolute permanent black hole of classical relativity to the evaporating mortal black hole of quantum field theory. You've seen how the restless energy of the vacuum, stirred by the fierce gravitational gradients at the horizon, must inevitably lead to a slow leak of mass and energy. But if we stop here, we are left with a universe that is, in a profound way, broken. A universe where information is destroyed, where the past becomes fundamentally unknowable, where black holes are cosmic shredders that burn the library of reality to produce meaningless thermal noise. This was Hawking's bet for decades. But the universe has a habit of being more clever, more consistent, and more deeply interconnected than we can initially imagine. The big unifying truth is not just that black holes evaporate. It is that they must evaporate in a way that preserves the information of what fell in. The two ideas are not in conflict. They are two sides of the same coin. To see why, we have to take all the pieces we've gathered and let them click together. Let's go back to the central tension. On one hand, we have the no-hair theorem of classical general relativity. A black hole is mass, charge, and spin, nothing else. On the other hand, we have the quantum principle of unitarity. Information is never destroyed, only transformed. Hawking's calculations seem to force a choice. Either general relativity is wrong at the horizon, or quantum mechanics is wrong forever. For years, physicists divided into camps, but slowly a third possibility emerged from the shadows. What if both theorems are correct, but our understanding of the situation is flawed? What if the mistake is assuming that an observer who falls into a black hole and an observer who stays outside can both have a consistent, simultaneous description of the same events? This leads us to a revolutionary principle inspired by the lessons of quantum mechanics itself, black hole complementarity, proposed by Leonard Susskind and others in the 1990s. It states that the experience of the infalling observer and the experience of the outside observer are both valid in their own frames of reference, but they cannot be combined into a single, objective picture without violating a fundamental law. It's like the wave-particle duality of an electron. Asking, is it a wave or a particle, is the wrong question. It is both, and which description you use depends on what you are measuring. Similarly, complementarity says for an observer outside, the information of what fell in is not lost behind the horizon. It is smeared, scrambled, and eventually radiated back out in the Hawking radiation, but in an incredibly complex encoded form. The horizon is a place of tremendous, but not infinite energy density. It is a stretched horizon, a chaotic quantum membrane that stores and processes information before re-emitting it. But for an observer falling in according to the classical principle of equivalence, crossing the horizon should be an uneventful local experience. There is no firewall, No burning wall of energy, at least not according to the classical picture. Complementarity reconciles this by stating that the two perspectives are complementary descriptions of the same reality. They cannot be communicated between the two observers because any attempt to do so would require sending a signal that violates a core limit like the speed of light or quantum uncertainty. The information, therefore, exists in two places. From the outside view, it is on the horizon and in the radiation. From the inside view, it is falling toward the singularity. This is not a contradiction if no single observer can ever access both copies. The universe, in its deepest logic, forbids the paradox from being experimentally realized. This is the first part of the unifying truth. Evaporation does not imply erasure. The black hole is not a terminal endpoint. It is a transformer. It takes ordered information, scrambles it into what looks like random thermal noise to any simple probe, but retains the potential for it to be decoded in principle. The radiation is not truly random. It has subtle quantum correlations, threads of cause and effect woven between the emitted particles over the black hole's entire lifetime. Decoding it would require a computer larger than the universe and a time longer than its age, but the information is, in theory, there. This preserves the sanctity of quantum mechanics. Now, let's take the final breathtaking step. Why is evaporation inevitable? Not just because of the math of quantum fields in curved space, but for a deeper, more structural reason. It comes back to entropy and the second law of thermodynamics. Jacob Bekenstein's wild idea was correct. The area of the event horizon is a measure of the black hole's entropy. But entropy is not just a number. It is a count of the number of microscopic ways a system can be arranged on the inside while looking the same on the outside. For a black hole to have entropy, it must have internal states, a vast number of possible quantum configurations that all correspond to the same mass, charge, and spin. What are these configurations? They are the quantum gravitational microstates of the horizon itself. This is where modern theory, particularly string theory and the holographic principle, has provided a stunning visualization. The holographic principle, strongly hinted at by the work of Gerard Hooft and Susskind, suggests that all the information contained within a volume of space can be represented as a theory painted on its boundary surface. For a black hole, this means all the information about everything that ever fell in is not lost in the singularity, but is encoded on the event horizon, a two-dimensional surface storing a three-dimensional reality. The entropy proportional to the area is literally the informational content of that surface. Now, tie this to thermodynamics. Any system with entropy and a temperature is subject to the laws of thermodynamics. If it is alone in a colder environment, it will radiate heat to reach equilibrium. A black hole has a temperature. Universe specifically, the cosmic microwave background at 2.7 Kelvin is a bath. For a black hole colder than 2.7 Kelvin, which all stellar mass and larger black holes are, it absorbs more energy than it emits, but the universe is expanding and cooling. In a trillion years, the cosmic background will fade to near absolute zero. At that point, every black hole will be warmer than its surroundings, and by the inexorable logic of the second law, it must then radiate its energy away into the colder void. It must evaporate. Its horizon area must decrease. Its entropy must eventually be carried away by the radiation. But here is the beautiful unifying punchline. As the black hole evaporates, the information encoded on its shrinking surface doesn't vanish. It is transferred bit by quantum bit into the correlations of the outgoing radiation. The process is like burning a densely encoded DVD. The smoke and ash seem random, but if you could collect every atom and trace its trajectory back to the moment it left the disk, you could, in principle, reconstruct the movie. The black hole is that disk, and Hawking radiation is the smoke. The evaporation is the playing of the movie, frame by frame, into the universe. Therefore, the opening claim that black holes evaporate was not the full truth. The full truth is more profound. Black holes evaporate because they store information. Their mortality is a direct consequence of their role as quantum informational systems. The classical picture of a permanent, information-destroying sink was not just incomplete, it was a contradiction in terms. A universe with permanent black holes would be a universe where entropy could be permanently hidden, where information could be deleted, where the arrow of time could be broken. Our universe, built on quantum logic and thermodynamic flow, cannot tolerate such an object. So it doesn't. It gives black holes a temperature. It gives them a lifespan. It makes them temporary processes of reality, not eternal graves. This is why Feynman's approach is so vital here. He taught us to look for the minimal, essential mechanism that makes something inevitable. Not just the math says so, but the world couldn't work any other way. The unsettling theory that collapses your mind isn't just that black holes glow. It's that their glowing mortality is the signature of a deeper holographic unity, a universe where the fabric of spacetime itself is a quantum information network, and where even the darkest pit must eventually confess everything it knows in a whisper of particles to an empty and listening sky. And so, we find ourselves here at the end of this long path, looking back at the dark patches between the stars with new eyes. The journey we took began with an impossible claim that the universe's ultimate vaults are leaking, evaporating into nothing. It was a statement that defied our deepest intuitions about power, permanence, and the nature of nothingness. But intuition, as we've seen, is a story told by our limited senses. It is a story written in the language of medium-sized objects moving at medium speeds. It is a story that breaks down completely at the edges of reality, at the quantum foam, and at the event horizon. The true story of the universe is written in a different language, a mathematical and logical poetry where emptiness is fertile, where horizons encode memories, and where even death by gravity is a transformation, not an end. This is the recurring theme of physics at its deepest level. Truth is not always comfortable. The truth about our place in the sun-centered solar system was uncomfortable. The truth about the mutability of space and time was uncomfortable. The truth that solid matter is mostly empty space, held together by fleeting particles, is uncomfortable. And the truth that black holes, those symbols of finality, are ephemeral quantum objects, shining their histories away over eons, is profoundly unsettling. It dismantles our fairy tales of monsters and eternal prisons. It replaces them with something more sophisticated, more nuanced, and infinitely more beautiful. The beauty is not in the grim darkness, but in the delicate, inevitable process of revelation. A black hole is not a villain. It is a consequence. Its evaporation is not an anomaly. It is a signature. It is the universe signing its own work, proving that the laws of the very small and the very large are not at war, but are threads in the same seamless fabric. This revelation forces us to confront a humbling and magnificent idea. Reality is not what it seems, but it is consistent. It follows rules, even in the most extreme environments imaginable. Where our everyday logic shatters, a deeper logic takes over. The principle that information cannot be lost is not just a technical rule of quantum mechanics. It is a statement about the connectedness of all events. It says that the past matters. It says that every piece of the universe, from a photon to a galaxy, carries with it a thread that leads back to the beginning. A black hole does not cut those threads. It weaves them into an impossibly complex knot, a knot that slowly unravels itself through Hawking radiation. The universe forgets nothing. This is why we do physics, not to collect dry facts, but to engage in this grand detective story, to follow the clues, the paradoxical stability of atoms, the bending of starlight, the faint thermal glow of empty space wherever they lead, even if they lead us to conclusions that collapse our minds. The journey itself is the reward. The moment of connection, when a dozen scattered ideas click into a single coherent picture, is a feeling of understanding that is as close to magic as this world allows. Now, I have a question for you, a personal one. After this long journey, what part of this changed how you see reality? Was it the idea that emptiness is alive? That acceleration can create heat from nothing? That the horizon is a quantum computer? Or was it the final unifying thought that evaporation is the price the universe pays for remembering? I am genuinely deeply curious. Drop a comment below and tell me. This conversation, this shared exploration, is the entire point of Think Beyond Physics. Your thoughts and questions fuel what we explore next. And if this journey gave you that rare feeling of seeing the world differently, please share this video with one person. Share it with someone who loves a good mystery or who thinks they know what a black hole is. Share it because challenging common misconceptions is how we all think broader. The biggest misconception of all is that topics like this are only for experts in ivory towers. They are not. They are for anyone with patience and curiosity. You have just proven that. For those who have been here throughout this exploration, thank you. Your attention is the most valuable thing in the world. If you haven't subscribed yet, please consider doing so. This channel is a commitment to taking the time that deep understanding requires. No shortcuts, no surface-level draws. Our next ultra-deep dive is already in the works. We will be taking apart another pillar of intuition, another obvious truth about reality that, upon closer inspection, reveals a hidden world of wonder. I can't wait to share it with you. Until then, keep looking at those dark patches between the stars. But see them now not as nothing, and not as eternal prisons, but as temporary sculptures in space-time, slowly, patiently, whispering their secrets back into the light. This is Think Beyond Physics. Thank you for thinking with me.